Article 408.15a of the National Electrical Code prohibits connecting more than one circuit to a multi-pole disconnect switch. Article 408.17e requires each circuit to be individually fused or circuit breaker protected. Jumpering a disconnect pole to create multiple circuits is generally not legal. There are safety concerns with doing that. If one of the circuits fails, it could overload the other circuit and create a fire hazard. The jumper can create a weak point in the system which could lead to electrical arcs and potential shock hazards. Instead of jumpering the disconnect pole, a subpanel should be installed with multiple circuit breakers. This will provide each circuit with its own fuses or circuit breakers, ensuring proper protection and preventing overloading. To make the bond safe, firstly remove the jumper from the disconnect pole. Secondly, install a subpanel with 15 amp circuit breakers. Thirdly, connect each circuit to the subpanel. Fourthly, label each circuit clearly for easy identification and troubleshooting. It is additionally recommended that the barn be inspected by a licensed electrician to ensure compliance with all relevant electrical codes and safety standards. A qualified electrician can also assess the existing 20 amp breaker in the barn and determine if it is appropriate for the new load. The National Electrical Code, or NEC, is a set of standards that govern electrical installations in the United States. Its purpose is to ensure electrical systems are safe and reliable, reducing the risk of fire and electrical shock. Several key articles within the NEC address the safe and correct wiring of electrical systems. Article 210 covers branch circuits, which are the circuits that extend from the final overcurrent device protecting the circuit to the outlets. This article specifies requirements for the number and type of outlets, the ampacity of conductors, and overcurrent protection. Article 215 focuses on feeders, which are the circuits that carry power from the service equipment to a subpanel or other distribution point. This article outlines requirements for feeder sizing, overcurrent protection, and grounding. Article 220 provides guidelines for calculating the load on the electrical circuits. Accurate load calculations are crucial for selecting the correct size conductors and overcurrent protection devices, preventing overloads and ensuring safe operation. Article 230 covers service entrances, which are the conductors and equipment used to bring electricity from the utility company to the building. This article specifies requirements for service conductor size, overcurrent protection, and grounding. Article 250 addresses grounding and bonding, which are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, tripping the overcurrent device and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of shock. Article 300 covers general wiring methods, which apply to all types of electrical installations. This article specifies requirements for conductor installation, support, and protection. Article 310 provides tables for determining the allowable ampacity of conductors. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. Article 408 focuses on switchboards and panel boards, which are used to distribute electricity throughout a building. This article specifies requirements for the construction, installation, and overcurrent protection of switchboards and panel boards. Article 430 covers motors and motor circuits, which have specific requirements due to the inrush current that occurs when a motor starts. This article outlines requirements for motor circuit conductors, overcurrent protection, and control equipment. These NEC articles are essential for ensuring electrical installations are safe and compliant. Adhering to these standards reduces the risk of electrical hazards and protects people and property. A subpanel is a secondary distribution panel that receives power from the main electrical service panel and distributes it to individual branch circuits. Subpanels are used to extend the capacity of the main panel and provide additional circuit breakers for new or expanded electrical loads. When installing a subpanel, several key steps must be followed to ensure safety and compliance with electrical codes. Firstly, choose an appropriate location for the subpanel. The location should be dry, accessible, and have sufficient space for the panel and its wiring. Secondly, determine the size of the subpanel needed. This depends on the number and size of the circuits that will be connected to the subpanel. Calculate the total load of the circuits and select a subpanel with a sufficient ampacity rating. Thirdly, install a grounding wire from the main electrical panel to the subpanel. This grounding wire provides a path for fault current to return to the source, tripping the overcurrent device and preventing electrical shock. Fourthly, run the feeder wires from the main electrical panel to the subpanel. The feeder wires should be sized according to the calculated load and protected by an appropriately sized circuit breaker in the main panel. Fifthly, connect the feeder wires to the main lugs in the subpanel. Ensure the connections are tight and secure. Sixthly, install the circuit breakers in the subpanel. Select circuit breakers with the appropriate ampacity rating for each circuit. Seventhly, connect the branch circuit wires to the circuit breakers in the subpanel. Ensure the connections are tight and secure. Eighthly, label each circuit breaker in the subpanel. This makes it easy to identify and troubleshoot circuits. Ninthly, test the subpanel to ensure it is working properly. Use a multimeter to verify the voltage and current in each circuit. The NEC provides specific requirements for subpanel installations. Article 408 covers switchboards and panel boards, including subpanels. This article specifies requirements for the construction, installation, and overcurrent protection of subpanels. Article 250 addresses grounding and bonding, which are essential for electrical safety. The grounding system must be properly installed to provide a low impedance path for fault current to return to the source. Article 310 provides tables for determining the allowable ampacity of conductors. The ampacity of the feeder wires must be sufficient to carry the calculated load. Installing a subpanel can be a complex task. If you are not comfortable working with electricity, it is best to hire a qualified electrician. An electrician can ensure that the subpanel is installed safely and in compliance with all applicable codes. A circuit breaker is an overcurrent protection device that automatically trips and interrupts the flow of electricity when a fault or overload occurs. Circuit breakers are designed to protect electrical circuits from damage caused by excessive current. There are several types of circuit breakers commonly used in residential and commercial electrical systems. Firstly, standard thermal magnetic circuit breakers are the most common type. They use a bimetallic strip that bends when heated by excessive current, tripping the breaker. They also have a magnetic element that trips the breaker quickly in response to a short circuit. Secondly, ground fault circuit interrupters, or GFCIs, are designed to protect people from electrical shock. They monitor the current flowing in the circuit and trip the breaker if they detect a difference between the outgoing and return current, indicating a ground fault. Thirdly, arc fault circuit interrupters, or FSIs, are designed to protect against fires caused by arcing faults. They detect the unique characteristics of arcing faults and trip the breaker to prevent a fire. Circuit breakers are rated by their ampacity, which is the maximum current they can carry continuously without tripping. Circuit breakers are also rated by their voltage, which is the maximum voltage they can safely interrupt. When selecting a circuit breaker, it is important to choose one with the appropriate ampacity and voltage rating for the circuit it will be protecting. The NEC provides specific requirements for circuit breakers. Article 240 covers overcurrent protection, including circuit breakers. This article specifies requirements for the selection, installation, and protection of circuit breakers. Article 408 covers switchboards and panel boards, which house circuit breakers. This article specifies requirements for the construction, installation, and overcurrent protection of switchboards and panel boards. Article 430 covers motors and motor circuits, which have specific requirements for overcurrent protection due to the inrush current that occurs when a motor starts. When a circuit breaker trips, it is important to determine the cause of the trip before resetting the breaker. Common causes of circuit breaker trips include overloads, short circuits, and ground faults. An overload occurs when a circuit is carrying more current than it is designed to handle. This can be caused by plugging too many appliances into a single circuit or by a faulty appliance. A short circuit occurs when a wire carrying current comes into contact with a neutral wire or a ground. This creates a very high current flow, which trips the breaker quickly. A ground fault occurs when current leaks from a live wire to ground. This can be caused by damaged insulation or by a person coming into contact with a live wire. Circuit breakers are essential for electrical safety. They protect electrical circuits from damage and prevent electrical shock and fires. An electrical disconnect is a device used to isolate an electrical circuit or piece of equipment from its power source. Disconnects are used for safety purposes, allowing workers to safely perform maintenance or repairs on electrical equipment without the risk of electric shock. There are several types of electrical disconnects, each designed for specific applications. Firstly, fuse disconnects incorporate fuses that provide overcurrent protection for the circuit. When an overcurrent occurs, the fuses blow, interrupting the flow of electricity and protecting the equipment. Secondly, non-fuse disconnects do not have fuses and are used to isolate circuits that already have overcurrent protection. Thirdly, manual disconnects are operated by hand and are typically used for low-voltage applications. Fourthly, automatic disconnects are operated by a control system and are used for high-voltage applications. Electrical disconnects are rated by their voltage and current carrying capacity. The voltage rating indicates the maximum voltage the disconnect can safely interrupt, while the current rating indicates the maximum current the disconnect can carry continuously. When selecting an electrical disconnect, it is important to choose one with the appropriate voltage and current rating for the circuit it will be isolating. The NEC provides specific requirements for electrical disconnects. Article 430 covers motors and motor circuits, which have specific requirements for disconnects. This article specifies requirements for the location, type, and rating of disconnects for motor circuits. Article 600 covers electric signs and outline lighting, which also have specific requirements for disconnects. This article specifies requirements for the location and type of disconnects for electric signs and outline lighting. Article 620 covers elevators, dumbwaiters, escalators, moving walks, wheelchair lifts, and stairway chair lifts, which have specific requirements for disconnects. This article specifies requirements for the location and type of disconnects for these types of equipment. Electrical disconnects must be installed in readily accessible locations so they can be easily operated in case of an emergency. They must also be clearly labeled to indicate the equipment they disconnect. When working on electrical equipment, it is important to always use the proper lockout/tagout procedures to ensure the equipment is de-energized and cannot be accidentally energized while work is being performed. Lockout/tagout procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect to prevent it from being turned back on. Electrical disconnects are essential for electrical safety. They allow workers to safely perform maintenance and repairs on electrical equipment without the risk of electric shock. A qualified electrician is a professional who has the knowledge, skills, and experience to safely install, maintain, and repair electrical systems. Electricians undergo extensive training and must pass a licensing exam to demonstrate their competence. There are several types of electricians, each specializing in different areas of electrical work. Firstly, residential electricians work on electrical systems in homes. They install wiring, outlets, lighting fixtures, and other electrical components. Secondly, commercial electricians work on electrical systems in businesses and other commercial buildings. They install and maintain complex electrical systems, including power distribution systems, lighting systems, and control systems. Thirdly, industrial electricians work on electrical systems in factories and other industrial facilities. They install and maintain heavy-duty electrical equipment, such as motors, generators, and transformers. Electricians must have a thorough understanding of electrical codes and safety regulations. They must also be able to read blueprints and wiring diagrams. When hiring an electrician, it is important to choose one who is licensed and insured. A licensed electrician has met the requirements set by the state or local government to ensure they are qualified to perform electrical work. An insured electrician has insurance to protect you from liability if they are injured while working on your property or if their work causes damage. Electricians perform a wide range of tasks, including installing wiring, outlets, and lighting fixtures, troubleshooting electrical problems, repairing electrical equipment, and inspecting electrical systems. They use a variety of tools and equipment, including wire strippers, pliers, screwdrivers, multimeters, and voltage testers. Electrical work can be dangerous, so it is important to hire a qualified electrician to ensure the work is done safely and correctly. If you are not comfortable working with electricity, it is best to leave electrical work to the professionals. An electrical inspection is a thorough examination of an electrical system to ensure it is safe and compliant with electrical codes. Electrical inspections are typically performed by licensed electrical inspectors who are trained to identify electrical hazards and code violations. There are several reasons why you might need an electrical inspection. Firstly, when buying or selling a home, an electrical inspection can help identify any potential electrical problems that need to be addressed. Secondly, when renovating or remodeling a home, an electrical inspection can ensure that the new electrical work is done safely and correctly. Thirdly, when experiencing electrical problems, an electrical inspection can help identify the cause of the problem and recommend solutions. During an electrical inspection, the inspector will examine all aspects of the electrical system, including the wiring, outlets, lighting fixtures, circuit breakers, and grounding system. The inspector will look for potential hazards, such as damaged wiring, overloaded circuits, and missing ground connections. The inspector will also check to see if the electrical system is compliant with the NEC and other applicable codes. After the inspection, the inspector will provide a written report outlining any findings and recommendations. The report may include a list of repairs that need to be made to bring the electrical system up to code. Electrical inspections are essential for electrical safety. They help to identify and correct electrical hazards before they can cause a fire or electrical shock. The NEC is a comprehensive set of standards for electrical installations. It is updated every 3 years to reflect the latest advances in electrical technology and safety practices. Compliance with the NEC is essential for ensuring electrical systems are safe and reliable. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for all aspects of electrical installations, from the service entrance to the branch circuits. The NEC is used by electricians, electrical inspectors, and other professionals involved in the electrical industry. It is also used by building officials to ensure that electrical installations are compliant with local codes. The NEC is published by the National Fire Protection Association, or NFPA. The NFPA is a non-profit organization that develops and publishes codes and standards for fire safety and electrical safety. The NEC is adopted by most states and local jurisdictions in the United States. It is also used in many other countries around the world. Compliance with the NEC is not only important for safety, but it can also help to reduce insurance costs and avoid legal liability. Electrical systems that are installed in accordance with the NEC are less likely to cause fires or electrical shocks, which can save lives and property. The NEC is a valuable resource for anyone involved in the electrical industry. It provides the information needed to design, install, and maintain safe and reliable electrical systems. Grounding and bonding are two essential safety measures that protect people from electric shock and prevent fires. Grounding provides a low-impedance path for fault current to return to the source, tripping the overcurrent device and disconnecting the circuit. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of shock. Grounding and bonding work together to create a safe electrical system. Grounding provides a path for fault current, while bonding ensures that all metal parts are at the same potential. There are several types of grounding systems used in electrical installations. Firstly, the most common type is the equipment grounding conductor, or EG, which is a wire that connects the metal parts of the electrical system to the grounding electrode. Secondly, the grounding electrode is a metal rod or plate that is buried in the earth and provides a connection to ground. There are also several types of bonding methods used in electrical installations. Firstly, the most common type is the bonding jumper, which is a wire that connects two metal parts of the electrical system together. Secondly, bonding can also be achieved by using metal conduit or other metal raceways as the bonding path. The NEC provides specific requirements for grounding and bonding. Article 250 covers grounding and bonding in detail. This article specifies requirements for the size and type of grounding and bonding conductors, as well as the methods for installing them. Grounding and bonding are essential for electrical safety. They protect people from electric shock and prevent fires. It is important to ensure that grounding and bonding systems are properly installed and maintained. Overcurrent protection is a critical safety measure that protects electrical systems from damage caused by excessive current. Overcurrent protection devices, such as circuit breakers and fuses, are designed to automatically interrupt the flow of electricity when a fault or overload occurs. Overcurrent protection devices are rated by their ampacity, which is the maximum current they can carry continuously without tripping or blowing. When selecting an overcurrent protection device, it is important to choose one with the appropriate ampacity rating for the circuit it will be protecting. The NEC provides specific requirements for overcurrent protection. Article 240 covers overcurrent protection in detail. This article specifies requirements for the selection, installation, and protection of overcurrent protection devices. Overcurrent can be caused by several factors, including short circuits, overloads, and ground faults. A short circuit occurs when a wire carrying current comes into contact with a neutral wire or a ground. This creates a very high current flow, which can damage equipment and cause fires. An overload occurs when a circuit is carrying more current than it is designed to handle. This can be caused by plugging too many appliances into a single circuit or by a faulty appliance. A ground fault occurs when current leaks from a live wire to ground. This can be caused by damaged insulation or by a person coming into contact with a live wire. Overcurrent protection devices are designed to protect against all of these types of overcurrent. They are an essential part of any electrical system. Electrical safety is paramount when working with or around electricity. Electricity can be dangerous and can cause serious injury or death if not handled properly. There are several basic electrical safety rules that everyone should follow. Firstly, never touch electrical wires or equipment with wet hands. Water is a good conductor of electricity, so touching electrical wires or equipment with wet hands can create a path for electricity to flow through your body, causing an electric shock. Secondly, never overload electrical circuits. Overloading a circuit can cause the wires to overheat and start a fire. Thirdly, never use damaged electrical cords or equipment. Damaged cords or equipment can expose live wires, which can cause an electric shock. Fourthly, always use the proper tools and equipment when working with electricity. Using the wrong tools or equipment can damage the electrical system and increase the risk of electric shock. Fifthly, always turn off the power before working on electrical equipment. This will prevent you from getting an electric shock. Sixthly, always call a qualified electrician for any electrical work that you are not comfortable doing yourself. Electrical work can be dangerous, so it is best to leave it to the professionals. There are also several safety devices that can help to protect you from electric shock. GFCIs are designed to protect people from electric shock. They monitor the current flowing in the circuit and trip the breaker if they detect a difference between the outgoing and return current, indicating a ground fault. SIs are designed to protect against fires caused by arcing faults. They detect the unique characteristics of arcing faults and trip the breaker to prevent a fire. Surge protectors are designed to protect electronic equipment from voltage spikes. Voltage spikes can damage electronic equipment and cause it to fail. Always follow these basic electrical safety rules and use the proper safety devices to protect yourself from electric shock. Electricity is a powerful force that should be treated with respect.